let's look at a typical titration problem. All right. Now, sodium hydroxide is a solid if it's pure, but we don't usually weigh it out when we want to know a specific amount of sodium hydroxide. Anybody know why that is? Why can't you just weigh out pellets of sodium hydroxide? I've heard that issue before. They have a property that it's called that they're hygroscopic. Do you know what that means? What is something that is hygroscopic? It's something that absorbs water from the air. So like, you ever have new shoes or something and they have those little silica gel packets in them? You know what I'm talking about? Or sometimes food has it in there, beef jerky and stuff. That's another example of that. Those little packets are hygroscopic, so they absorb water out of the air. They prevent that environment from getting too moist. So sodium hydroxide does the same thing. And in fact, if you leave a pellet of sodium hydroxide out on the desk, and you come away and you come back in a little bit, you'll notice that it will have turned into a little puddle. That's not because it melted, but it's because it absorbed enough water from the air that it's effectively dissolved itself in condensing water. And it's actually pretty dangerous because it looks like a little droplet of water, but it's actually this super corrosive sodium hydroxide. So we don't measure sodium hydroxide because you can't really reliably know that it's anhydrous, that it doesn't have water in it. As soon as it touches the air, it has water in it, unless you're doing it in a very special environment called the glove box, where you have no water in this whole box and you put your hands in these big gloves and do it that way. You can't prevent it from getting water. So when we measure things with sodium hydroxide, as we will be doing tomorrow in lab and then in this leaf lab, we have to standardize the sodium hydroxide. And that means that we're going to use something that we can measure very precisely and measure the sodium hydroxide against it. And that's this example right here. One thing that we often use as a standard is something called potassium hydrogen phthalate, which is an acid of sorts that has one acidic hydrogen, which means that it can transfer one hydrogen to a base to make water. So we're going to look at this particular sample of potassium hydrogen phthalate, which we can call KHP. It's not phosphorus. It's this molecule of phthalate. And you measure out this KHP, which you can measure out very precisely, then dissolve it, and then standardize it or measure it against the sodium hydroxide. And depending on how much sodium hydroxide you use, that will help you figure out how much, what the concentration of the sodium hydroxide was. So the goal of this type of a procedure is to calculate the condensation or the concentration of the sodium hydroxide solution. We can't get the concentration just by measuring out the sodium hydroxide because of this water issue that we talked about. So we have to know how much sodium hydroxide is actually in the solution. And this is a technique that's done all the time in any kind of lab, you know, from EPA labs to food analysis labs to quality control labs and all kinds of different companies. If you ever find yourself in that sort of environment, that sort of a business, there will be people standardizing things for titrations to try to analyze stuff. Our lab staff do it all the time and just preparing solutions and things like that. So it's a really important step. Let's look at how that works. First, we need an equation, a chemical equation. So we got to figure out what's going on. The potassium hydrogen phthalate is the acid, and that's going to react with sodium hydroxide. And let's figure out what that forms. We're going to say KHP plus aqueous NaOH. And we're told that this has one acidic hydrogen, which means one hydrogen can go from the KHP to the NaOH. And so that's going to look like this. We're going to have H2O, right? Typical acid-base reaction. That's the net ionic product. And then you're going to have this weird ionic product, NaKP, which is really just ions of sodium, potassium, and phthalate. If we look at the full ionic equation here, we might say K plus H plus, and I'm going to get rid of that C because this is going to be confusing because it's not phosphorus. That's the ion, this C8H4O4, that's phthalate. And then our products are going to be water and Na plus and K plus and this C8H4O4. So things that are spectators are those guys, and the net ionic is just the H and OH is water, just like any other acid-base reaction. So kind of a weird molecule here, but it's still a typical acid, you know, just as though that were HCl or something. Same thing's happening. That also tells us that this equation is balanced. Everything reacts in a 1-to-1 ratio. That's another reason that we use KHP to standardize NaOH. Makes the calculations really easy because it's just a single hydrogen. Okay, so now we need to look at some of the numbers and figure out what's going on here. And let's see, for space concerns, I'm going to delete this ionic equation just so we can go back to looking at the standard equation and get our numbers together. Okay. All right, so we're told that we dissolve 1.3009 grams of this. And we essentially want to know how much of this would we use in the equation. For a titration, you are you're adding this phenolphthalein. Have you guys used that before? Anybody done titrations with the phenolphthalein where it turns pink when you get the stuff combined? Did you do that in previous chemistry classes? No? Okay. We'll do it tomorrow. Don't worry about it. Anyway, it's the stuff that, it's called an indicator, which just means it changes color. And it changes color right around neutral pH. Changes from clear, from colorless to pink. So when you do a titration, you're adding the base to the acid. And at first, the solution of your acid, it has a very low pH. And then as you add base, the pH rises and the pH rises. And then when you get to that equivalence point where there's exactly the exact molar amount, all of a sudden you're neutral and the stuff turns pink. If you go too far, it gets dark pink, and then you're past the equivalence point. Then you've added excess base. So the goal of the titration is to add just enough base to neutralize the acid and no extra. And we're going to talk about the actual physical technique of how you do that tomorrow in lab. It's a little tricky, takes a little practice, kind of like the pipettes, but you'll get it. So at the equivalence point, that's the stoichiometric point. That's the point at which we have the same number of moles of KHP and NaOH. And that's why titrations are useful, because you can measure out a certain amount of, let's say, KHP. If you add sodium hydroxide until it's neutralized, then you know that you have exactly the equal molar amounts. If you add too much sodium hydroxide, you've got an excess. That's not going to work. If you don't add enough, then you have an excess of the other one. That's not going to work. So you want exactly equal molar amounts. All right. So if we have that, assuming we did this correctly, how many moles of sodium hydroxide will we have added to neutralize the KHP? How would you figure that out? Yeah, so it's just, so this is the part where it's just a standard mole type calculation. We're going to convert the KHP to moles, and then we need the same number of NaOH to react with it. So they're helping us out a little bit here. We're told the molecular weight, so we don't have to add up all that KHC8H4O4 stuff. It's just 204.22. So we can say 1.3009 grams of KHP. And KHP is 204.22 grams per 1 mole. And so it's going to be 6.3701. You mind if I use millimoles instead of moles? Is that going to mess you up? If you don't like that, think of it as 6.3701 times 10 to the minus 3 moles. It means the same thing. All right, so that's how many moles of KHP we've added. Then how many moles of NaOH will there be at the equivalence point? The same, right? Okay, so if we've gotten to that exact equivalence point, we know that we have added exactly 6.3701 millimoles of sodium hydroxide. Now we can figure out the concentration of sodium hydroxide because we're also told the volume. So let me grab a burette actually so I can show you what this looks like and how we get that volume. Have you used these things before? We haven't used these this semester yet, have we? But you've seen them before, maybe? Some people not. Okay. This is called a burette. B-U-R-E-T. Lots of people try to be fancy and pronounce it burette, but that's actually not correct. It's a burette. Maybe it once was a burette, but it changed. I don't actually know the history of that, so just making stuff up. Anyway, let's take a look at the scale, because the scale on a burette is a little bit different from what you might be used to on something like a graduated cylinder. That's not going to work. I'll get a white piece of paper. All right, so what's weird about this scale compared to, say, a graduated cylinder?
It goes down.
Yeah, it goes down instead of up. You see that? It starts at 0 at the top, and it goes down to 25 at the bottom. So does that mean you have to subtract from 25 every time you make a measurement? Not exactly. This type of a instrument is made for dispensing a certain amount of liquid. So the way that you use a burette is you mark the starting point and the ending point, and then you subtract. In other words, you fill this out. You don't always, we'll talk about this again tomorrow, but there's kind of a misconception that you're supposed to fill up the burette to 0 and then like count from there of how much comes out. That's actually not great because it takes a lot of wasted time to get it exactly at 0, and the chance that you can get it exactly to 0 is not always great. So the better way to do it is to just fill this thing up to wherever it stops. You just kind of dump some in, read that amount precisely, say it's 4.23, and then you let some out with this little valve at the bottom. And as soon as you get to that equivalence point, you stop letting it out, and let's say that that comes out at 13.26, you'd subtract those two numbers, and then you know how much came out of the burette. And that way you're not wasting time trying to get it exactly to some even amount. So that's why the scale is the way it is. It doesn't actually matter because we're going to do that subtraction. But you do have to make sure that you're making the right recording or making the right measurement. Sorry, that's blurry, but it doesn't seem to want to focus anyway. So if your liquid level is here, you just have to remember that, okay, that's between the 1 and the 2, so that's going to be 1 point something. It's easy to make the mistake because we're used to graduated cylinders and say, okay, that's above the 2, so it's 2 point something, but really it should be read as 1 point something. All right, so keep that in mind for tomorrow. So we would take those measurements, and in this particular case, you'd need a couple burettes full because the amount that it took was 41.20 milliliters, and that got to that pink equivalence point. So with those two pieces of information, can you figure out the concentration of sodium hydroxide in molarity? Maybe, maybe not. What's molarity?
Moles per liter.
Moles per liter. So we've got moles and we've got liters. Do we have to do some conversions with this first to get moles and liters? We don't, because we have millimoles and milliliters. So moles per liter is the same as millimoles per milliliter. All right, so we can say 6.3701 divided by 41.20 is going to be 0.1546 molar. So we standardize the concentration, and we know exactly what the concentration of that sodium hydroxide is. Usually what we would do in a titration type experiment is we would then take that sodium hydroxide and use it to measure some unknown acid. So you'd standardize the sodium hydroxide first, then use it to measure some unknown acid. The unknown acid we're going to use tomorrow is acid that's been partially neutralized by an antacid tablet. So the antacid tablet partially neutralizes the acid, and then you titrate to figure out how much acid is left unneutralized. And I think tomorrow we don't have to do this. I think we're, just because of time constraints, we have sodium hydroxide that's already been standardized by our staff. And you'll notice it is standardized to usually several significant figures. When you standardize a solution like that, you really want to know exactly how many moles per liter, because you're often using pretty small amounts. So you really want a precise measurement of the concentration. And we usually, you'll see tomorrow, but we usually have our sodium hydroxide solution standardized out to 4 or 5 or 6 significant figures, so that they make good measurements. So you feel like okay about this? You'll get some practice with this in the lab tomorrow. I don't think there's any pre-lab. Has anybody looked at it? I don't think there was any kind of pre-lab. So just in lieu of a pre-lab, please read the lab carefully so that you're ready to go and ready to do it, because there are some new procedures and stuff in it. All right, while we're talking about calculations, before we get into gases, is anybody having trouble with the limiting reactant calculations from the lab? Yes? Okay. Where are you having trouble with it?
I'm so confused until I have an answer.
All right, let's quickly go over what happened in the lab and how we might go through those calculations. I'm not going to go through all the calculations for you, but at least kind of get you started. So remind me, what was the reaction again? It was zinc something and iron something. Zinc.
One of them was phosphate and the other was sulfate.
Yeah.
Yeah, let me look at it.
Which one was which?
Sodium phosphate and then zinc sulfate.
That's right. Sodium phosphate and zinc sulfate. And that formed sodium sulfate, and I'll highlight this, zinc phosphate precipitate. And that's the solid product that you collected. All right, so this is not balanced. So let's balance that. That works, okay. All right, so there was the equation. And one thing that I think helps, maybe if you're trying to look through these calculations or work through them, is just let's take an example of what we might have started with and how that would have played itself out in the in this reaction. So let's say, I don't know what the initial mixes were, but the initial thing that you got, the initial powder, was some mix of sodium phosphate and zinc sulfate, right? So let's say it was, and you weighed out what, like 2 grams of it? Is that right? All right, so let's say that that initial 2 grams that you weighed of this stuff, let's say it was 0.5 grams of this and 1.5 grams of this. Just, you know, to make something up. So if those two reacted and they form some amount of precipitate, and we can go through and do the stoichiometric calculations to figure that out. But the issue here is one of these is going to be a limiting reactant, I assume, that those even numbers I picked are not going to be the exact stoichiometric ratio. So one of those is going to be a limiting reactant. All right, so let's say that, well, let's calculate it out. I'm going to show you a little trick, especially for those of you who are still working on your homework. Now, obviously, you have to be able to do these calculations for the exam, and so you're not going to have the help of this. But has anybody ever used this before? Yeah, works pretty well, right? Yeah. So if you want to do some lab calculations with this, I don't have any problem with you taking shortcuts as long as you actually still know how to do it. Can we agree on that? But watch what you can do with this if it works. You can say 0.500 grams of Na3PO4. And if it works, it will convert it to moles for you. Isn't that handy? It'll tell you the mass composition, it'll tell you the molar mass, it'll tell you melting point, all kinds of other stuff, as long as it's a chemical that it recognizes. But that can be really handy if you're trying to do a bunch of these calculations, because you don't have to add up a bunch of molar masses and potentially introduce errors and all that sort of thing. Again, you still have to know how to do those things, like for the exam, but when you're working on lab or something, this can be very handy. All right. So that tells us that this is 3.05 millimoles. And we can see if we can do the same with the other. 1.5 grams zinc sulfate. Always check it to make sure it actually finds the right thing. 9.29 millimoles. Actually, that should be 9.290. All right, so can you tell which is the limiting reactant from that? All right, if not, then let's calculate it away. It's probably the sodium. Yeah, let's calculate it out and check. So that tells us that we would need 4.575 moles of zinc sulfate. Do we have that? Yes, we have well more than that, so that would be in excess. Okay, so let's say that this is what happened, and these two things reacted. How would you calculate how much precipitate you made, or you would expect to make? Right, you use the limiting reactant. So you'd use the 3.05 millimoles, basically do the same thing we just did, but for zinc phosphate instead. So 3.05 millimoles. And this time we've got 1 mole of precipitate per 2 moles of Na3PO4. And since we want to know grams, we'll also multiply that by the molar mass of zinc phosphate, which we can use our handy thing for here. You can also type out the word. That usually works too. Nope, didn't like that one. There we go. So zinc phosphate is 386.1. Whoops. 3.05 divided by 2 times 386.1, 588.8. Whoops, milligrams, sorry. That's the only problem with using millimoles. You got to make sure you keep your milli all the way through. All right, so we calculated based on this that we should get that many grams of precipitate if that's what our starting mixture was. Now, you don't know what your starting mixture is, so we've got to go backwards. You know this number, right? Because that's what you measured. Now, that's not going to be exact because you got an actual yield, not a theoretical yield. But it should be pretty close. This reaction should be pretty good, and if you did it right, and you did careful filtration and recovered everything, you should get most of what you would expect. So then you can work backwards from there and say, all right, well, let's convert that to moles and then solve how many of the beginning stuff we must have started out with. The last part of the calculations then is figuring out the limiting reactant. Because you don't know, let's say you got 0.5888 grams. You could back calculate this and find that you should have started with 0.500 moles of this, but you would, or 500 grams of this, but you would not get 1.500 grams of this because that's in excess. So how did we figure out in the lab which one is in excess? Yeah, that was that test with beaker 1 and 2. We took some of, after the reaction was done, you took some of the liquid in beakers 1 and 2, and that would have had the excess reagent in it, whichever one it is, because it didn't react, so it's still in solution. So the excess one would have precipitated with when you added more of the other one in it. So let's say you had beakers 1 and 2, and in this case, that beaker 1 and 2 would have had zinc sulfate in it, because that's our one that's in excess. So it would have had leftover zinc sulfate dissolved. So then when we added some sodium phosphate, we would have seen it get cloudy because we're precipitating the excess back out. So that's how you know, once you know which one's in excess, you know the other one was limiting, then you can do your calculations, and whatever was left over from the original amount goes with the excess.
So the limiting is the one that had no reaction?
Well, it depends how you think about that. The solutions had the excess left over in it. So whichever one made a precipitate was the opposite one. So I would just draw it. I would just draw it and keep it straight. So like, here's 1, here's 2. In our example, the stuff that's in here, or here, which one were we supposed to, which one got added in 1 and which one got added in 2? Or was it different for everybody? Did it just say keep track of them? All right, so this is sodium and zinc sulfate. Like that? Okay. So in our case, which one would have turned cloudy? The first one with the sodium phosphate being added, or the second one with the zinc sulfate being added? The first one, yeah. Because we know that that the zinc sulfate was in excess. So that means what was in here was excess zinc sulfate. Zinc sulfate's not going to do anything when you add more zinc sulfate, but it is going to do something when you add sodium phosphate. So rather than thinking of like, well, if we add this, that one's the limiting, draw it out like this in both possible scenarios, because either there's zinc sulfate left in solution or there's sodium phosphate left in solution. See what happened to yours, and then that'll tell you what was left over, depending on which one got cloudy. Okay. Once you know that, then you can finish the calculations, because then you'll know that all the leftover mass from the initial amount was zinc sulfate, or was whatever one was limiting, zinc sulfate, or excess with zinc sulfate in our example. Does that help? Calculations for this coming lab, by the way, will also be sort of complicated, so make sure you give yourself enough time to go through them and ask questions if you get stuck. All right, let's talk about gases. You know some things about gases?
PV equals nRT.
PV equals nRT, that's a good one. Has anybody else heard that before? Yeah, it's been happening before. What else do you know about gases? Anybody have gas right now? Have issues? Eat too much cabbage this morning? Hoods. That's what the hoods are for. In lab, if when you walk by the hoods, just take care of it. The hoods will just make it go away. All right, so let's talk about some gases. We're going to kind of split this chapter up into a couple parts. The first part I find a little bit less interesting. The second part I find a little bit more interesting. That's just me. The first part is going to be talking a little bit about the mathematical relationships between different gases, the PV equals nRT. How do pressure, volume, and temperature, and number of moles interact with each other when we talk about gases, and how is that different from solids and liquids? It's fine. It's interesting. It's revolutionary science when it was developed, but it's just filling in some equations. The second part talks about what's called the kinetic molecular theory of gases. So remember how we talked about the difference between laws and theories? Anybody remember the recap of that? What was that difference?
Laws are what happens and theories are why they happen.
Yeah, laws are what happens and theories are why they happen. So first, we're going to look at all the laws. You may have heard of some of them: Boyles law, Charles law, the ideal gas law. These are just things that happen. You have a sample of gas, you do this to it, this other thing happens all the time. The second part, we're going to talk about the kinetic molecular theory, which says if we assume that this is what gases are made of and this is how they behave, then we can expect all these properties, and we can use that theory to explain the properties that we observe. And I think that's interesting because it makes you kind of think about what's happening at a molecular level instead of just remembering a bunch of equations and plugging things into them. So, all right, let's talk about our units first. We're going to talk about pressure. We haven't talked about pressure before. What is pressure? I mean, it's up there, but do you know what pressure is? Anybody? Have you heard that term? So what is it? What is it to you? If you didn't see this, and I said, what's pressure? What would you say?
Pounds per square inch.
Okay, pounds per square inch. So that's a unit of pressure. So what is that describing?
The force applied to the area.
Right, a force applied to an area. So a force applied to a particular amount of space. These are the units of that force, but we can think a little bit about what makes higher pressure or lower pressure. So things like a smaller area will make higher pressure versus a larger area, even with the same force. A good example of that is like shoes. Has anybody here ever worn like high heel shoes? I have. They if you're wearing high heel shoes versus flat shoes, you have the same amount of force because you're the same person, you have with the same weight. But what happens if you walk with high heel shoes like in the grass or in the dirt? You ready? Yeah, you like sink in if your heels are sharp enough. Yeah, you sink in. So even with the same force, you're going to sink in because you've got a greater pressure on that area. If you have flat shoes, that force is spread out over a greater area, and so it's not going to be as great of a pressure. So we measure pressure in the atmosphere is something called a barometer. You heard about barometric pressure? Barometric pressure comes from this type of an instrument where basically you have this tub full of mercury, which is not safe, so we're not going to have a tub full of mercury. And you invert a column and evacuate all the air out of it. So there's no air in that column anymore. If there's no air in there, the mercury will fill it up based on the atmospheric pressure pushing on that pool of mercury and then pushing the mercury up the column. The higher the atmospheric pressure is, the further up that column the mercury can get pushed. And you measure that in millimeters, and that's why we have this pressure measurement called millimeters of mercury. It's kind of a weird measurement because we don't usually think of pressure as millimeters, but it's millimeters of mercury that get pushed up this column at sea level. So at sea level, we call that standard atmospheric pressure. And here it is in some different units. 1 atmosphere, 760 millimeters of mercury, or torr, and then 101,325 pascals. Some of the English units, inches of mercury, and then pounds per square inch. Where do we see pounds per square inch? You've probably heard that pressure before, PSI. Where might we measure pressure in PSI? Tires, yeah. Always check your tire pressure, right? When's the last time you checked your tire pressure? Recently, hopefully. Check it, now and then. So yeah, tire pressure, things like gas pressures, or if you heat your house with steam or something like that, you might see those pressures. What about inches of mercury? Where do we use inches of mercury? It's really the same thing, but with that scale is in inches. But we actually use that as a common pressure measurement. Do you know where you see that?
Weather.
Yeah, that's the weather pressure. Like if they talk about a low pressure versus a high pressure system, or that the barometric pressure is going down versus going up, that's usually reported in inches of mercury. If you have one of those barometers you put on the wall with a thermometer, it probably has a little dial, and it's like around 28 or 29. A neat way to look at this, there's this site, Weather Underground. It has a neat way of displaying weather information right here. I really like this because it gives you a whole lot of information in one quick snapshot. But what you have is a long, what is that, a 9-day forecast or something. You have temperature plotted here, so up and down as day or night. So you can quite easily and quickly see what the long-term temperature trends are going to be. And then this graph is plotting the barometric pressure. So you can see it's like around 30 inches of mercury right now, which is a relatively high pressure. And then that pressure is going to dip down here. And usually when the barometric pressure dips, that's when we start to see a chance of rain, chance of storms. And that's what these blue boxes are, the chance of rain. So as that pressure goes down, the chance of rain tends to go up, so you can see where to expect rain. And then this is kind of a cool graph that plots both the wind speed and direction at the same time. So you can see where the wind's coming from, and also if it's going to be more windy or less windy. I really like graphs like this where you get a whole lot of information, like just in one thing instead of just a giant bar or something. But anyway, that's where we might see barometric pressure, and that's given in inches. Remember that that is inches of mercury, not just inches, like, because inches is a length, obviously. Okay, so you should know these numbers. I don't care about the other ones. I'll give you conversions if you need for the other ones. But you should know that 1 atmosphere is 760 millimeters of mercury, or 760 torr. So that's going to be important when we start doing some of these calculations. The pascal, we didn't really talk about the pascal. That's actually the official SI or metric unit of pressure. That is a Newton per square meter. Newton is a force measurement per square meter. So that's kind of the a common pressure measurement more in physics, really. So we can do some conversions of this. I don't think we need to go through that. You're just converting units just like any other unit conversion. So let's talk a little bit about these laws. We're going to look at 3 laws: Boyles, Charles, and Avogadro's law. You've probably heard these before. And we're going to look at first Boyle's law, which is pressure and volume. And I like to look at it kind of conceptually, and then we'll go back to the equation. If you're more math-oriented, the equation might be helpful for you. But basic idea of Boyle's law is as pressure increases, volume decreases. So pressure and volume are inversely related. One goes up, the other one goes down. If you have a container of gas, you increase the pressure on that gas while keeping the volume of while keeping the temperature the same. The volume has to, what did I say? Increase the pressure of the gas. The volume has to decrease, and the same for the opposite. So here's an example of that. If you push a weight on a certain sample of gas that's sealed, you increase the weight, that pressure has to go up. Or you increase the pressure, that volume goes down. So you've made it smaller. This is a pretty intuitive one. And the thing you can think about is squeezing a balloon. You squeeze a balloon, it gets smaller, right? No one's ever going to say you squeeze a balloon, it's bigger. So that's kind of the easy way of remembering this. You squeeze a balloon, you increase the pressure, and you decrease the volume. All right. The way that looks in an equation is PV equals K, which means pressure times volume is constant. Another way we might look at it is a couple of different ways. Is pressure equals a constant divided by volume. So that shows that inverse relationship. As one goes up, the other one has to go down. And then another way we might write it is P1 V1 equals P2 V2, which means if you have an initial pressure and volume and you change one, you can calculate the other one because the product of those two has to stay the same. So you can have something like this. Sulfur dioxide is found in the exhaust of automobiles and power plants. Consider a 1.53 liter sample of gaseous sulfur dioxide at a pressure of 5.6 times 10 to the third pascals. If the pressure is changed to 1.5 times 10 to the fourth pascals at a constant temperature, what will be the new volume of the gas? So you can see what is the new volume. First, we should always think about this conceptually and think about what is happening. So if the pressure goes from 5.6 times 10 to the third pascals to 1.5 times 10 to the fourth pascals, is that an increase or decrease of pressure? It's an increase, yeah. 10 to the fourth is bigger than 10 to the third, so it's an increase in pressure. So what would we expect the volume to do? Decrease. So we should at least keep that in our head that when we do this, we should find a lower volume. If we find a higher volume, we probably did something wrong, we should go check it. So we'll say P1 V1 equals P2 V2. Now, do we have to convert units here? Does this equation only work for particular units of pressure and volume, or can we just leave them in the units that they're in?
Work for any unit as long as they're consistent.
Yeah, it's because as long as they're consistent. Because you'll notice it's the same thing on both sides. That's the equality. So as long as your units stay the same, it's fine. That's not always the case. When we get into temperature, we'll see that it has to be in Kelvin for it to work. But for this type of a relationship, we can leave the units as they are as long as they're the same on both sides. So our initial pressure is 5.6 times 10 to the third pascals. And our initial volume is 1.53 liters. We're going to solve for, our final pressure is 1.5 times 10 to the fourth pascals. And then we're going to solve for the final volume. All right, so 0.571 liters is going to be our new volume. And we check that. Yes, that's less than the 1.53 we started with. Doesn't mean it's right necessarily, but at least it doesn't kind of raise that flag that we must have done something wrong. Okay, next relationship between temperature and volume. So here's kind of a plot of that. As temperature goes up, volume goes up. Now these are different amounts of gases. So we have to have the same amount of gas, and we have to be at constant pressure. Because if you change pressure or you change amount of gas, now you're changing too many things. And we actually can do problems where we change all this stuff, but that's how we'll use this combined gas law that we'll talk about in a little bit. So this shows temperature increasing, volume increasing, a direct relationship between temperature and volume. The kind of tricky thing about this, not really tricky, but you have to make sure to do this in kelvins. Why do you think that is? Yeah, because you can't go negative. The negative screws up the proportional relationship. And so if you have, and you can try this, this happens all the time. If you try to do this without converting to Kelvin, the proportions can get messed up, and you'll end up with an answer that doesn't make sense. So we have to make sure to convert to Kelvin when we do these types of problems. So why don't you do that and see if you can solve this sample problem that is very similar to what we just did. Now, to do this, you're going to have to rearrange this equation, which says the volume is proportional to temperature times a constant. Another way of writing this then is that volume divided by temperature is constant. So volume divided by temperature stays the same. Given that, see if you can calculate the new volume as a gas is heated from 15 degrees to 38 degrees. Can we get it?
liters.
2.79 liters, we think. Is it different? Same. Right, let's get it. So we're going to look at saying that this stays the same, volume over temperature stays the same. So that means that volume 1, 2.58 liters over temperature in Kelvin, which in this case is 288 K, equals this unknown second volume at 38 C, which is 311 K. Is that right?
Yeah.
Yeah, 311, okay. So V2 is going to be 0.58 times 311 divided by 288. 2.79 liters. Great, thanks. If you have trouble with these kinds of manipulations of solving kind of some of this algebra, it might be something to go back over from your math class. Just make sure that there's a lot of stuff in this chapter of being able to rearrange equations and solve for different variables. So if that's something that you have trouble with, you might want to refresh on that as we work through this. So the last one we're going to talk about of these relationships, there's actually a fourth one also. We don't really need to talk about it separately, but Avogadro's law notes that if you have more gas, you need more volume. This is probably the most obvious of all. If you add more gas, then it's going to take up more volume if the pressure stays the same. In other words, if you fill up a balloon, you put more helium in the balloon gets bigger, assuming it stays the same pressure. Now, the thing that is a little bit weird about this, or a little bit different about this, is that this is based on the number of moles, not the mass of the gas. Why do you think that is? Essentially, what this is saying is that the same number of gas molecules of, let's say, helium, a tiny little thing, the same number of moles, same number of atoms of helium in a balloon is going to take up the same space as the same number of moles of radon in a balloon. Radon is 222 versus 4. So why do you think that is? Why don't we do this by mass? Why isn't more mass going to make more volume in a balloon? Why is it only moles?
Because a mole tells you how much space that gas takes up.
Well, it tells you how many atoms there are.
Yeah.
So then why is that what is proportional to the space it takes up rather than the size of each particle? You know what I'm saying? Like, why doesn't the size of each atom matter?
Because all of that mass is inside the nucleus. The nucleus is so small compared to the rest of it that it doesn't actually change the size that much.
Right, and we're going to extend that even a little bit further. That yes, the mass is in the nucleus, but even if we consider the mass in the atom, the size of an atom of gas is so small compared to the space between gas molecules that it's essentially insignificant. So we can basically say that the volume that individual gases take up, the volume that individual molecules take up is insignificant because a gas is mostly space. The volume is almost entirely space and only a little bit taken up by the actual atoms themselves. So the size or the weight of the atom is not really significant because, again, that really doesn't affect the volume compared to the spaces between the molecules or atoms or whatever. So even if you have some giant gas molecule, like, well, I mean, gas molecules aren't that big except at high temperature, but even if you had, say, like butane or something, which is a relatively big molecule with multiple carbons and stuff, we would still say it takes up that same kind of gas space. Now, we will talk about some exceptions when we get to the end of this, some corrections to where that does become an issue. But for our purposes, for general gas behavior, we can assume that any gas is going to have the same behavior, and it doesn't actually matter what it is. What will change, of course, is the mass, so the density will change, but it does not affect the volume. All right, so now you got an equation just like we did before, V equals AN, so there's a direct proportion, or direct relationship between volume and number of moles. So see if you can rearrange that question yourself to solve a problem like this. Suppose we have a 12.2 liter sample containing 0.5 moles of oxygen gas at a pressure of 1 atmosphere and temperature of 25 degrees C. If all of this oxygen were converted to ozone, what would be the volume of the ozone? So oxygen is a gas, O2. Ozone is a gas, O3. if everything else stays the same in terms of temperature and pressure, what is the new volume after this reaction? In other words, how has the number of moles changed? See if you can figure this out. I'll give you a hint. You're going to need a balanced equation, balanced chemical equation. Okay. Let's have a party outside. Does anybody get the chemical equation for this? What would that look like? I mean, it's pretty simple, but it does have to be balanced. Yeah. So then how does that affect the volume? Based on our equation here, we can say that these things are directly proportional. So if we increase the number of moles, the volume should increase. If we decrease the number of moles, the volume should decrease. So what have we done? Have we increased or decreased the number of moles? We've decreased it. Is that what you said? We said decreased. Okay, that's right. We've gone from 3 to 2. Where there were 3 moles of oxygen, there are now 2 of ozone. So 3 moles of gas gone to 2 moles of gas. And that means that our volume will probably decrease. So we've got, we start with 12.2 liters and 3 moles. Then we end with, oh, I'm sorry, not 3 moles, half a mole, right, 0.50 moles. Then we go with, if it's 3 to 2, then it's half a mole to 2/3 of half, which is right, a third. So that 12.2 liter sample would go down to 8 liters. If you had a volume, a 12 liter balloon full of oxygen, which would be a pretty big balloon, and all that oxygen were converted to ozone through photolysis or some kind of way, that balloon would get smaller. Because now those oxygen atoms are going to be closer together because more of them are in, because they are in O3 ozone molecules instead of O2 oxygen molecules. So you've decreased, even though you haven't changed the mass at all, got the same amount of mass in there, but because you've decreased your number of moles, the number of gas particles, you've decreased the volume. So the last piece of this is to put this all together, and that's what we call the ideal gas law. It's just a combination of all of these together, and the constants all get combined into something called the universal gas constant, which you should know. Now, the universal gas constant comes in a couple different types of units depending on what system you're working in and what kind of stuff. So sometimes you'll have to convert units. But the one that we'll use mostly is this one, which is 0.08206 liter atmospheres per Kelvin mole. And then if we rearrange this all together, we get what we talked about at the beginning, PV equals nRT. Pressure times volume is going to equal the number of moles times this gas constant times temperature. Now, what units you need for this are given by the gas constant that you're using. So if you're remembering this gas constant, 0.0821 or 0.08206, then you need to make sure that your volumes in liters, your pressures in atmospheres, your temperatures in kelvins. If they're not, you can convert them, or you can keep them the same and convert the units in the gas constant. But they have to be the same so that they can cancel each other out. On the right side, you see R here, and N and T. So the Kelvin and moles cancel, and you have liter atmospheres, which is the PV on the other side. That's why there's such kind of a weird collection of units in there. And this way, we can solve all kinds of problems like these, which we won't do right now, but we'll come back to this next week. Sample of hydrogen gas has a volume of 8.56 liters, blah, 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 calculate the moles of H2 present. So this time we know volume, we know temperature, and we know pressure, so we can calculate moles. If given enough of those quantities in the ideal gas law, assuming an ideal gas, you can calculate the others. A more interesting way of doing these kinds of problems is using this in stoichiometry. So we can now talk about the pressure and the volume of gas produced or used in a chemical reaction. It's especially important for measurement purposes because you often use pressure to measure a gas. You'll see if we do some stuff with gases, like when we go into the, use the ICP machine, gases are usually measured in pressure. And partial pressures, and that we can use this kind of equations to figure out moles and figure out how that would actually work in a reaction. So we'll be doing some of that next week. I think the homework for this is up. I think it's set to be due on Monday night as usual, but I'll push that back because obviously we haven't finished this chapter yet. So get started on that stuff. The math part of this chapter is not super tricky, so it should be pretty much more the same. But then tomorrow, be ready for lab. Make sure you read through that in acid lab so you know what we're doing. And it should be fun.